Okay, I'm going to try to keep this quick. We have kind of a cool math fact that we have to go through. It's going to be it's not really vector specific, but it's something that will come up in the vector section a fair bit. So we have this Cartesian plane in front of us, a coordinate system where we have an x value in the horizontal, a y value in the vertical, and we can kind of draw a cute little grid here with unit squares. If I look to represent any other line in this system or any other vector specifically in this system, I can do it in terms of my two axes. In this case, we don't necessarily think of it this way, but I've really got 1, 2, 3, 4, 5, 6, 7 values this way, or 7 times this vector right here. Sorry, that wasn't very good, but you get the idea. If there's a single vector going this way, I need 7 of those to get across. And then I have 1, 2, 3, 4, 5 sort of these flipped around and made smaller. Okay, so essentially I have 5 of those vectors. And together, 7 of these and 5 of these get us to the point where we have this vector here as a 7, and we can represent it as 7, 5. So essentially what we're doing is we're writing this vector in terms of these. I need 7 of those, or 7 times this one, plus 5 times this one, to kind of form the existing, or the vector that I want. Same sort of thing happens with any other point, with any other vector, sorry, hitting any other point. If I go this way, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4.5 maybe, so -6 and 4.5. And again, what that's saying is I need 6 of these turned around, so -6 of those, and I need 4.5 of these to go up this way. So no cool fact so far, but the cool fact is the coordinate system we chose there, we chose out of convenience and simplicity. But any line in 2 dimensions can be represented in terms of any 2 other lines. That's to say, as the sum of a fraction of the other 2 lines. Okay, so I chose a unit vector here, 1 unit going to the right. I chose a unit vector here, 1 unit going to the north or going upwards. But I could have just as easily, or maybe not just as easily, but I could have also chosen this to be my set of axes. And I can write any other vector in this 2-dimensional space in terms of an amount of this and an amount of this. Now, it won't necessarily be 2, 3, 4, 4.5. It might be a third or quarter or 0.28 times as much. But the fact is I can still do that. Okay, so if I take, I'll just make one here that's relatively easy, I think, although I don't know what's going to be easy. So if I'm looking to represent this vector here in terms of these other 2, I need my vector to go from the tail of this one, so that seems like a reasonable way to go, and to the from the tail of the orange one out this way and then back towards the head of this one. So if I kind of line this up like this, that was a really poorly chosen example. Let's just shrink that a little bit so that it doesn't look like I intended it to work that way. Essentially, I now needed to go, oh, I didn't want to do that. I wanted to go this much in this direction. So let's just sort of make a number up and say that that's 80% of the way. So it's maybe 0.8 of that vector. And then I need to go this direction about 55%, so let's say 0.55 of that vector. And so this vector here is actually 0.8 of the one plus a certain amount of the other to represent it. Now, if we had chosen a line that was a little bit more difficult, a little bit messier, well, actually, let's just make it simple, I guess. What if I had chosen this one? You can see that essentially I should be going from the the bottom of this one towards the top of this one. And so now I'm looking at the same distance here, except I'm actually going in the negative direction. So in the second case, make this so we'll keep the orange one there. We'll make this green one. So for the green one, I'm looking at starting off this distance, but again in the negative direction. So I've got negative 0.55 of u, and then minus or plus negative 0.8 of v. So I'm going this direction, same distance essentially, this direction, same distance as well. So this can be written in terms of parts of the other two. Now in some cases, obviously if my initial line here had been much smaller, if it had been something like this, I might have had 2 of these, or 2.5 of these, as was the case with the regular coordinate axes. We picked nice small numbers of, a distance of 1 on the other one to make it easy. In this case, we have to deal with whatever we have. So, the math here, if we're actually doing this question, represent the vector v in terms of a and b. Essentially what it's asking me to do is write v as some number times the vector a plus some number times the vector b. And the way it works out is, okay, sorry, just rewriting it here, putting in the values. This can be written in terms of those. But what happens will, or what will happen is that my x values will be determined by the other x values. My y values will be determined by the other y values. And so even though we're sort of leaving the xy coordinate to some extent, we're still going to use that mentally to sort of make associations here. So my 3 will be some value times 2 plus some value times negative 4. That seems like a silly way to write that. So minus 4t. My negative 5 will be determined by a certain amount of the 7 minus a certain amount of the 8. And so essentially now I have two systems, two equations, two unknowns, and I can solve it as I would in grade 9. I'm going to pause now so that you don't hear the announcements as they come on, and I will finish up while you're waiting. Okay, so finishing up here. To solve the system of equations, we have two equations with two unknowns. We can use substitution or elimination. I did it with elimination. I changed my 2s and my 7s, or s7 to 2s and 7s. So of course, that's what you would do anyways. I wouldn't have written them that way, except that I'd already sort of done it. So elimination, we multiply the first equation by 2. And now it's 6 equals 4s minus 8t. Again, this is grade 9 math, so if you need to, can go back and take a look. I'm not going to go over it too extensively. And then basically I subtract from equation 2. So negative 5 minus 6 is negative 11. 7s minus 4s is 3s. And s is 11 thirds. Sorry, negative 11 thirds. Substitute that into either one of the original equations. Doesn't matter which one. And I use the first one, it looks like. Basically simplify after that. and we find that S was this, T was this, and so our final answer is that vector V is equal to negative 11/3 of vector A minus 31/12 of vector B, or plus negative if you want to. I wrote it originally with the vector numbers in, but this is the cleaner answer at the end.